Hello. So today I'd like to talk to you about dividing radicals. And before we do anything, I just want to talk about a basic property of dividing radicals that hopefully won't be too surprising to you based on what we've done with multiplying radicals before. But if we have two radicals like this and we're showing division through fractional notation, if you think back to when we did something like this with multiplying, if we had square root of 8 times square root of 2, we were able to put them together under one radical and have it written like this. So square root of 8 times times 2, all under one radical. That same property that applies for multiplication also applies to division. And so in a case like this, we can say that this square root of 8 divided by square root of 2 is the same thing as the square root of 8 divided by 2. All right, so we can put them under one radical. That's advantageous to us because sometimes we can cancel out any common factors we have. So for example, here, this would become square root of 4 because I would take a 2 out of each of them. And square root of 4 is easy for us to do. That's just 2. So sometimes before we do anything else with dividing radicals, it's helpful to just simplify them if they are in their fractions. So again, that comes from putting them together under one radical and canceling. But now that you know that's true, I could also just do it right from here and say, if I put them together under one radical, I would be able to divide out by 2. And then I would just simplify like that. So that's also another option, but this is the reason why, is because we can put them together under one radical just like we could do with multiplication. All right, that's one point that I want to bring out to you. The second point is something that is really going to be the bigger deal, and that is, as in all other areas of math, there are definitely math fashion faux pas, and one of them, I would say, that's a big one, is leaving a radical in the denominator. So let's say we had 3 over the square root of 5. Well, I would say I can't divide that like I did here. Again, I was able to do that division because both those, the 8 and the 2, were both innies. They were under the radical, but here I've got an outie, it's outside of the radical, and an innie, and I can't do anything. I would look at that, and you might look at that and say that's fully simplified. I can't do anything there. But one thing that we would say in math that is the fashion faux pas is you never leave a radical in the denominator. I don't really know how that developed, but all I can say is try saying that. Like, so you can say this fraction. All right, you would say this is 3/5. But how do you read that so it doesn't sound clunky? So 3 square root of fifths, it just seems kind of weird. And so if we were to remove that so that we had an integer or some sort of rational number in the denominator, that would be a little bit easier to read. I suspect that that's where it came from. And so we would just say this is not cool, right? We're not going to leave a radical in the denominator. So then the question you might have is, well, how do you remove it? So well, not a very good eraser here. All right, so let's start over with this. Let's say we have 3 over the square root of 5, and we would like to remove it. So think for just a second, what could you do to get rid of that radical in the denominator? All right, well, one guess, as you're screaming at me from home, one guess is that you would say, well, how about I just square it and do this? All right, that would certainly get rid of it. That would turn it into 9 over 5. But 3 over square root of 5 and 9 over 5 do not have the same value. All right, if we try that out, let me just write 3 over square root of 5 and 9 over 5, and let me do those on my calculator. Oops. Sorry, I should have had my better calculator ready. If I do 3 divided by the square root of 5, I end up with 1.34 and more. And then if I do 9 divided by 5, I end up with 1.8, right? So squaring this does succeed in getting rid of the radical, but it also changes the value. It's no longer the same value that we originally had. So that cannot possibly be what it is. All right, so let's try a second thing. All right, again, if you remember when we deal with fractions, especially when we talk about finding common denominators or things like that, anytime we do that, we have to multiply by something that is 1. All right, and again, we've said this can be the fanciest 1 that we want it to be. As long as the numerator and denominator are the same, then it's a 1. And so my next suggestion here is, or maybe your next suggestion here, I'm not sure if you would think of this, is what if I just multiply it by square root of 5 in the bottom? That does the same thing as squaring, right? Because if I do square root of 5 times square root of 5, that's like square root of 5 squared, and that would just give me 5. But now, instead of multiplying the top by 3, which would be fully squaring this, I'm just going to multiply the top by the same thing, right? So that I end up multiplying it by a 1, square root of 5 over square root of 5. So it will not change the value of this. It will just change the appearance and get rid of the square root in the denominator. So if I do that, in the bottom, square root of 5 times square root of 5, you could do this in one step and just say it's 5. You could do it in 2 steps and say, oh, that's square root of 25, which becomes 5. I don't really care. Either way is fine. I think probably when I was learning, I did this and then turned it into 5, but now I just go directly into turning it into 5. Right, in the numerator, we've got 3 times the square root of 5. Again, an outie and an innie cannot mix, so we just put them side by side to indicate multiplication. And now over here, I've got 3 square root of 5 over 5. Still not a lot easier to say, but now you could also maybe read it as 3/5 times square root of 5, which again would make this flow a little bit more naturally. Let's just confirm. We should get the value of this when I type it into my calculator to be the same as it was here, 1.34-ish. It was like 1.3416. So if I do that on my calculator and I get 3 times the square root of 5, divide it by 5, and I do get that same thing, 1.3416. So by doing it this method, right, by multiplying the denominator by something to get rid of the radical, in this case, namely itself, I get rid of the radical in the denominator, but I preserve the value of the original fraction. All right, so that is the strategy that we're going to take when we look at page 149 in your workbook. So if you could please have that out. I'm just going to use this right here. We're just going to go through and do some of the odd problems on this page. Right, so let's take a look at problem number 1. Right, now again, I've told you 2 things that you need to know about dividing radicals, and the first is that if we have 2 radicals right here, we can try to reduce them. I would generally do that as a first step unless something exceptional happened like this, where it was already a perfect square in the denominator, or here. But if it's not a perfect square in the denominator, I would try to simplify first by putting them together under one radical. So really, I can look at this as having a 1 out front. Right now, I'm just going to look at the outies together first. Sorry, my arm keeps catching on this paper. So I'm going to look at this as 2 parts. A rational part, 1/5, and then this irrational part, square root of 15 over square root of 20. Right. Later, you'll probably just not even write that separately. You'll just kind of ignore it until you figure out what this is. But for right now, let's break it up. All right. And then again, let's use that trick, the first thing I showed you on the other side, which is I can write this under a single radical. So this is 15 over 20. Right, now I'm going to go through and I'm going to reduce that. So we think to ourselves, what common factor do they have? All right, so they both have a 5. This becomes a 3. Oops, I was going to write a 5 and a 4. All right, so this is 1 over 5 times the square root of 3/4. Now, I said you can't have a radical in the denominator. You also can't have a fraction under a radical because there is a radical in the denominator then. Really, this is the same thing as square root of 3 over square root of 4. So we can't just leave it like that. So we're going to rewrite this as 1/5 times, and I'm going to bust it apart. Again, it was 2 separate things here. I pushed it together. I simplified, and now I'm going to break it apart again. So this is going to be square root of 3 over square root of 4. All right. Now, when I do that, you're able to see this, sorry. Okay, that's a little bit better. When I do that, then I can say, all right, again, there's no simplifying that needs to happen there. That's just a regular fraction that we've normally dealt with. But then this, I can't simplify the top. 3 is a prime, and so it's going to stay square root of 3. There's nothing I can take out of that. But square root of 4, that is a perfect square. It's the square of 2, and so I can take it out as a 2. Right? Now let me just combine it into a single fraction. And so 1 times square root of 3 is just square root of 3, and then 5 times 2 is 10. Right, and that is fully simplified. Right, now as we go along, we're going to start kind of keeping track of what it means to be fully simplified. Some things we already know, and some things we're just going to get as we go along. So the first thing, let me get back to this scrap paper that I had here. So in a list of when is a fraction with radicals fully simplified? All right, so the new one that we just got is no radicals in the denominator. Right, we want to get rid of all radicals in the denominator. If there are any radicals, it's not fully simplified. 2, and I'm just putting this because we know it already, is no perfect squares under any radicals. All right. So far, I think those are the only that we've talked about. If it's a fraction, though, then something that just kind of goes along that we would have talked about as soon as you started learning fractions, probably in like 5th grade or something, is make sure that the fraction is fully reduced. When we have radicals in our fraction, I'm going to say that a little differently. The outies are fully reduced. All right, and again, if we look back at this example that we just did, the outies are the things that are not in a radical anymore. That's the 1/5. All right, so if that were a standalone fraction, which it's looking like right now, if that were a standalone, is that fully reduced? And the answer is yes. And so we've automatically done that. Let's say that this had been a 2/10 or something like that. All right, then I would say, oh, that's not fully simplified. I have to simplify it to 2/5. All right, but again, that is not anything that deals with radicals. That's just fractions in general. So just don't forget that you are supposed to be doing that. All right. Okay, let's do another one together here. All right, so let's look at problem number 3. And again, we're going to use this same idea that we did before about just if I have 2 radicals that are being divided, can I simplify them? All right, so again, just as we did in the last one, I'm going to put these together under a single radical, and I'm going to reduce. All right, so what factor can you take out of both of them, and what will it become when you do that? All right, so hopefully you said, oh, I can take a 3 out of here and that's a 2, and I can take a 3 out of here and that's a 9. So this becomes the square root of 2/9. All right, now that I've fully reduced that fraction, just as we did before, I'm going to split it back up into individual radicals. So this is square root of 2 and square root of 9. And I'm going to look to see if I can simplify them independent of each other. All right, so square root of 2 is a prime. I can't do anything. And square root of 9 is just 3. All right, so I look at this and I say, is it fully simplified? Well, did I get all the radicals out of the denominator? Yep, there's no radical down there. Are the remaining radicals, which in this case is just the square root of 2, are there all the perfect squares removed from it? Well, yeah, 2 is a prime, so there are no perfect squares in there. And then the last part is, are all the outies simplified? And again, there's an implied 1 here, so really the outies make up a 1/3. If I had that as a regular fraction, I couldn't reduce it any further. Right? So that would be fully reduced. So all three things that we've said so far work. So we've got square root of 2 over 3 as our final simplified answer. All right, let's look at number 5. Now, number 5, you'll notice, is different from the first two that we looked at, where there were two radicals, one in the numerator and one in the denominator, being divided. Same thing here, one in the numerator, one in the denominator that were being divided, but here we just have that one radical in the denominator. So I can't cancel it out with anything. I would also look to say, hey, is there any way that that's a perfect square? Because that'd be an easy way to get rid of it. Right, but hopefully you're saying, nope, nothing I can do with 5. It's a prime, so I can't take its square, or I can't find a square within it. All right, so then we have to use the second thing that I told you about dividing radicals, and that is that fashion faux pas here, that we've got this square root of 5 down the denominator, which we're not allowed to have, and we need to get rid of it. And again, we talked about just a second ago about how we can't square it because it changes the value of it, but we could multiply it by a 1. And again, so we need some fraction here whose numerator and denominator are the same that will get rid of the square root of 5. All right, so square root of 5 will do that, because when I multiply square root of 5 by itself, it is like squaring just the square root of 5. But then to preserve the value, I'm going to make sure the numerator matches it so that it's a 1. Let me get rid of that 1 above because that looks weird now. All right, so the job of this guy is to get rid of the radical in the denominator, and the job of this guy is to keep the value of this fraction. It makes this a 1, which preserves the value of that. All right, so now let's just go across and multiply. All right, so 4 times the square root of 5, again, that's an outie, that's an innie. The best I can do is just put them right next to each other. So this becomes 4 times the square root of 5. And in the bottom, I've got square root of 5 times square root of 5. Again, you could do this in two different ways. You could multiply what's underneath there and get square root of 25, or you could just say square root of 5 times square root of 5 is 5. Right? Again, so you've got the choice that you could do square root of 25. You could do square root of 5 squared. Again, remember we said that when we see these two symbols together, they undo each other, which is how I got that 5 right there. Right, so then we ask the question, is it fully simplified? So we're looking for three things right now. We're looking, did I get rid of the radical in the denominator? Check. Are there any perfect squares under the radical that I have to remove? Nope, 5's a prime, so that is not, you can't simplify that. And then the third thing that we know so far is look at the outies and see if there's any simplifying we can do. Right, so can I simplify 4/5? Nope. So this is the final answer. All right, let's take a look at number 7 before things get really good at numbers 9 and 11. All right, so you might say, hey, cool, this looks like problems 1 and 3 that we did up top because there are two radicals in this one. But you're going to be a little bit disappointed because if you'll notice, in problems 1 and 3, when we combine them into a single fraction under a single radical, I was able to simplify, but here these are both prime and they will not cancel out like they did in the first two problems that we did. So doing this is really not helpful in this situation. All right, so I'm just going to cross that out. Sometimes you'll find that. So this is. Hey, sorry, it stopped recording and I kept talking. So I'm going to start back here where I was, and we'll just do it again. All right, so we can't simplify that. All right, so we've just got to go back to what we were doing in the previous problem, which is acknowledging that I need to get rid of that radical in the denominator. All right, so again, just like what I did in the previous example is I need to multiply this by itself. Essentially, I'm squaring it, but I'm only doing that to the bottom. All right, I can't square the whole thing where it changes the value. What I can do here is multiply this by a 1. All right, so we've got a square root of 3 in the top. Again, the denominator's job is to square that root 3 so that it turns into a 3. Again, it gets rid of the radical, but the job of the root 3 in the numerator is to make the value of this 1. All right, so let's go through and do this. All right, square root of 3 times square root of 3. Again, that's either square root of 3 squared, which would be 3. Square root of 3 times square root of 3 is square root of 9, which is 3. So however you want to think about that, the denominator is going to be 3. And then square root of 5 times square root of 3. You can do this in 2 separate steps if you want. You can do this as square root of 5 times 3. Or you can just skip right to the, I know that that's going to turn into square root of 15. So that it'll be square root of 15 over 3. Right? Then we need to check to make sure that it is fully reduced or fully simplified. So far we've got those 3 things that we're looking for. First is to make sure that we've got no radical in the denominator. Check. That's just a plain old 3. Second is to make sure that there is nothing under the radical that can be simplified. We cannot simplify this because it's just made up of 2 different primes, right? And so I can't take either of those out as a perfect square. And then the last step is to compare the outies. Again, this is an implied 1 right here, so this would be a 1/3. And say if 1/3 were a fraction, I could not reduce it anymore, so the outies are fully simplified. And so the final answer to this would be square root of 15 over 3. All right, fully simplified. All right, this is where things start getting good. All right. Well, it's all good, but this is where it starts to look visually more exciting. And that is now we have variables under the radicals too. All right, so that should not be scary too because we've done it before. What might be scary is that now it's in fraction form instead of either being added or multiplied that we've done already. So, but let's go back and let's just look in our first example that we did on this page. And if you remember, we had very similar to problem 9, we had a radical in the denominator, we had a rational number in the denominator. Wait, I can't remember if I said radical in the numerator or denominator. I have a radical in the numerator, I have a rational number in the denominator along with a radical in the denominator. And what we did here was we split it apart and then we put these 2 radical numbers together under 1 and simplified. All right, once we did that, then we busted it apart and went from there. So same thing is going to happen here. I'm going to break this apart. Again, there's an implied 1 here, so I'm going to break this rational fraction away from the rest of it. So then this becomes square root of 3x squared y cubed over square root of 5xy cubed. And now I'm going to do, the same thing I did up there, which is to put these together under 1 radical. All right, so 3x squared y cubed over 5xy cubed. All right, ignoring the radical, this looks exactly like what we did in chapter 6, which was simplifying using exponents. All right, and so this right here would be the quotient rule, where we could cancel things out. All right. The 3/5 is not going to change. That's just still a regular fraction. So I'm going to come down here and I'm going to start filling out what we have left. So 3 and 5. All right, now let's look at this. We've got an x squared over an x. All right, hopefully you remember from before, that's just going to turn into an x in the numerator. There's a couple different ways we could think about it. Is that I can say, well, the quotient rule says I just subtract the exponent, so 2 minus 1 is 1, and then I put that exponent on the variable wherever I started. So here I started up in the numerator, so this is just going to be an x to the first up top, or an x. Or you could just say, well, this is x times x, and this is x, and I'm going to cancel out one of the x's and leave one other x. All right, and then here with y cubed over y cubed, all right, you could say, well, let me subtract the exponents. 3 minus 3 is 0. So I would get a y to the 0 in the numerator. But remember, y to the 0 is just 1. All right, so that would just go away. Or you could just say right away, hey, when I have y to the third over y to the third, it's just 1. All right, so I've fully simplified the fraction that's under there now. And now let me do what we did again in the next step in problem 1, which was to bust these apart again. So I've got 1 over 4 times square root of 3x over square root of 5. Right? And then I need to get rid of the square root of 5. All right, so what would I do? Hopefully you said multiply top and bottom by square root of 5. Right, if you said multiply top and bottom by 4 square root of 5, you wouldn't be wrong, but let's focus on what the problem is. The problem is that irrational number in the denominator. That's the only thing we're trying to fix. There's no rules against having rational numbers in the denominator, thank goodness, otherwise we'd have a big problem. So really, I just want to take care of this, and the way I'm going to do that is just by multiplying it by itself. If I chose to do 4 square root of 5, I would have to do the same thing in the top. And if we think ahead what would happen, that would give me a 16 right here, and then that would give me a 4 up top, which would reduce to 1/4, which is right where we were right here. So it's not wrong to do that, it's just going to cause extra reducing for you in the end. So ultimately I would say avoid it if you can. If you don't, you'll see that you just have to reduce more. Okay, so let's go and do this then. The 1/4 is going to stay the same for right now. The square root of 3x times square root of 5 is going to give me square root of 15x. And then square root of 5 times square root of 5 is just going to give me 5. And again, I don't mind how many, if you want to take more steps than I do to do that, if you need to write that out, please do. Okay, so then here we are. And we've just got one more step to do before we check our final answer. So 1 times square root of 5x, that's just, I'm sorry, not square root of 5x, square root of 15x, that's just square root of 15x. And then right here, that becomes a 20. Okay, let's check it. So I'm looking to see, did I get rid of the radical in the denominator? Check, I did. Second is, are there any perfect squares under the remaining radicals? All right, so I need to look at 2 parts now. First, I need to look at square root of 15. All right, well, we just ran into square root of 15 just a minute ago, and we said that there's nothing I could do to reduce that, so that's going to stay. How about the x under here? Can that come out? Right, hopefully you remember from our previous conversations that the only way it can come out is if the exponent is higher than 1. Right? If it's just x to the first, it's not coming out. And even then, for it to come out fully, it would have to be an even exponent. Again, we did have odd exponents that we worked with, but we usually ended up leaving one of them behind. All right, so no, that can't come out either. And then we're going to look at the outies. Again, this is a 1 and a 20, and there's nothing that can reduce there. So our final answer is square root of 15x over 20. All right, last one. All right, this one offers something new, and that is the numerator is a binomial. All right, in every other problem that we had, the numerator just had one term. There was no plus or minus sign in there. Same. So this is a first for us that we have a binomial in the numerator. Again, I know based on experience that it's going to be tempting to do what we just did before, which was that we put these together under 1. But as soon as it's a binomial, that changes a little bit, right? Because we would have to do it to both of them, and that is not going to work. Because this does not have a radical in it. Again, what we would end up doing is we would simplifying this part of it, but leave this under the second one. Let me just show you. what you could do and tell you why it's not really that helpful. Right. So we could just unsubtract these two. All right. Again, remember when we have two fractions, as long as they have common denominators, we can put the numerators together and leave the denominator. So that's essentially, we had two separate fractions that combined into this. We could now simplify this one, right, and turn this into 3 over 4, and we could cancel out the a's and end up with square root of 3 over square root of 8. We would even be able to do more simplifying with that, but all of a sudden we now don't have common denominators anymore. So while we could do this, it's not going to leave us with a single fraction anymore. So I'm going to recommend not doing this. All right, so please don't do this. All right, and let's just focus on this. All right, so again, let's start here. 3 minus 3 square root of 3a, so many 3's, over 4 times square root of 8a. All right, I have another video for you to watch on the other side of this sheet, and I do the problem number 13 a little bit differently. So I'm just going to show you a method here, and then you can contrast it with the one in problem 13 so that you can see. So what I do in problem 13 is I simplify the denominator first by taking the 4 out of here and grouping it with, so this is square root of 4 times, square root of 4 times square root of 2. I take this square root of 4 out as a 2, and I would join it with this 4, so that would become 8 times square root of 2a. I'm not going to do that this time. You can watch it in problem 13 and just contrast it. But I just want you to see what happens if we leave this 8 in here unsimplified. It makes more work later on. You'll see in the next problem that it's a little bit faster to take out that the perfect square in there first. But let's not do that because I want you to see what's going to happen. All right, so again, this is the part that's a problem. All right, so I'm just going to multiply top and bottom by square root of 8a. Square root of 8a. All right, I just want to get rid of that radical in the denominator. And again, I'm making sure that this numerator and denominator match so that this is a 1, so it preserves the value of this. Now, the extra step, because this is a binomial, is you got to put parentheses around it. Right, because you got to make sure that you're distributing this 8a to each thing. If you don't do that, sometimes people just think you multiply the ones that are next to each other, but you're going to distribute like this. All right. In the numerator, when we take 3 times the square root of 8a, we just push them together, we get 3 times square root of 8a, minus, now we do it again, but here, because we do have a radical, I'm going to combine the things that are under the radical. So this is going to be a minus 3, and then 3 times 8 is 24, and a times a is a squared. So this is 24a squared. All right, in the denominator, I've got this 4 still, and then square root of 8a times square root of 8a is just 8a. All right, so when I put this together, I've got, in the denominator, I've got 32a. Sorry, this is going to run into this. You're going to end up doing these problems, the even ones, so you might want to start on a scrap piece of paper so that you don't use up the space that you have for this one. I, on the other hand, am going to keep using this space. All right, so now let's go through here. And we've got 3 times square root of 8a minus 3 times square root of 24a squared. Okay, so I asked myself the questions about, did I simplify? All right, so the first thing is, did I get rid of the radical on the bottom? Yes, I did. The second thing is, are there any perfect squares left under the remaining radicals? And because I didn't take care of this first by getting the perfect square out of here, there is still a perfect square under here and here. Right, so now I have to deal with it. If I thought I was taking a shortcut here, I've now just kind of expanded the problem because now the square root of 8a is showing up in 2 separate places that I have to simplify. All right, so when I do that, I'm going to break this. It's just the 8 that has a perfect square, so I'm going to break out a 4 from there. again, write as many steps as you need. This would look like square root of 4 times square root of 2a. All right, the 4 is going to come out as a 2 and join with the 3. So this will be 6 times square root of 2a. All right, minus, all right, let's do the same thing. There's a 4 in here, and this is also a perfect square. So I'm going to break it up as 4a squared times 6. All right, that 4a squared will come out as a 2a and join the 3. So this is minus 6a times square root of 6 all over 32a. Okay, so I'm going to go back again. Did I get rid of the square root in the denominator? Yes. Did I get rid of any perfect squares under the remaining radicals? Yes. Now, this part, again, our third step was, did I simplify the outies? Here, it's changing because it's a binomial in the numerator. So when I simplify the outies, I have to simplify all of them collectively. All right? So I'm looking to see, do all 3 of them share a common factor? Right? I know, based on experience with lots of students, I'm not necessarily saying you, but that the temptation is going to be to cancel out those A's. But again, it's got to be in all 3 of them. So I have to really be careful and look to make sure that I take out what is common only to all 3. So as I look at the 6 and the 32, just the number parts, I could say, oh, they all have a factor of 2 in them. So I can divide all 3 of them by 2, right? When I do that, this becomes a 3, this becomes a 3a, and this becomes a 16a, all right? Now you might say, well, what about the a's? Again, there's an a in here, and there's an a in here, but no a in here, so I cannot cancel the a's. So what's left then from here is 3 times square root of 2a minus 3a square root of 6 over 16a. Final answer. All right. Again, this is going to be a huge temptation to just cancel out some of the common factors, but you must make sure that you look at all of the outies. My suggestion to you is circle all of them so that you're sure you're working with all of them. All right, and then take out what's common to all of them. Again, notice that the thing that was canceled out was a 2, which is what would have come out if I had taken it out right here. Right, so I just actually, it's like spreading a virus, all right, which is maybe a little too sensitive right now. But that square root of 4 would have come out as that 2 that I ended up canceling in all of these places. All right, so my suggestion to you again, and you're going to see the contrast of this in problem 13, is take care of any perfect squares under your radical first, so that you don't spread it out to the rest of the problem and then have to simplify it later. All right, okay, so then that is the final answer, and that is the end of the video. All right, bye.